Hello, intro to stats class. Today we are going to do myths about chance behavior. It is starting from page number 411 to 418. So in this section they talk about three myths, and very first myth they talk about the myth of short run regularity. All right, so in this case usually uh, we talk about the randomness, where we say randomness is predictable in long run, but unfortunately usually uh, our intuition or intuition about randomness, it tries to tell that instead of long run we try to predict in a short run also. We feel like that if some kind of event happens, so this should be the next event for the given um, experiment. So what does it mean? We're going to look at two examples here. First example is example 7.4 that says what looks random. So basically, if you are tossing a coin and you're tossing it 6 times, if you tossed it a coin 6 times, so you know when you toss a coin, then you can have a toss a coin. You can have just two outcomes. It could be either head or tails. So depending on your 6 tosses, there could be two scenarios where you are either getting head tail, and head tail, head tail, tail head. This one, or you can get three tails in a row and then three tails, then three heads in a row. So, but when we look at it, we feel like this one is more random, kind of like it's alternating, but and we feel it's not random, it's just like it's repeating here. So our intuition says that's something not random, but actually that's very possible because uh, the coin, it doesn't know that what was the previous outcome, and based on whatever it had previously, it's not going to have the different outcome next time. So it's very possible that it could have this kind of pattern too. So this is equally likely to happen. But yes, when you do a long run, when you're doing the same thing, then we can think about that. Yes, in long run the heads and tail, they're going to be 50-50. So we can say that in long run heads and tails are equally probable. Says that about half a long sequence of tosses will be heads and half will be tails. So but in a short one you can predict it, okay? Because the coin, it doesn't have a memory. It cannot just register in its head that okay, last time it was heads, now it's going to be tail. All right, so let's take one more example here. So next example is example 7.5, where it talks about the hot hand in basketball. Basically, when there is some kind of recording of outcomes while playing basketball games. So sometimes people say that a specific player has hot hand. It means he's going to, or she's going to more likely make a shot or make a run, or just going to hit at the point. And then, but what happens, it's not the same, because in the short run we can say it, players, they perform consistently, not in streaks. If a player makes half her shot in long run, her hits and misses behave just like a coin, tossing a coin. Like when they play it, the player, or the way they play, it doesn't record anything. The events of getting the hits and misses, they're not dependent on each other. Like if you are having a hit once, then you're going to have a miss next time. So it's not predictable in short run, but in a long run, yes, you can say that it's going to be 50-50, like if a player has a hot hand, but you can predict in a short term. So the myth of a short term regularity, these two are the examples. So let's move to the next page. So here we're going to talk about myth of surprising meeting. So another myth of chance behavior is the myth of surprising meeting. It's basically here they talk about the Mr. Stans and his wife. They went for a vacation in Hawaii, and then what happened during some kind of recreation center or national park. They met there one of the student, Herbie. It was Mr. Stans, one of the former student, and they said, "Oh wow, how unusual! Maybe we were destined to meet." And but actually, it's not. It's important that here uh, it's uh, it's not surprising that they met, but yes, the certainly it's very unlikely that Mr. Stan is there uh, at the Volcano National Park visitor center that day, but meeting some non-contact during that day is not very unlikely, because usually a typical adult has 1500 casual acquaintances. And when we usually but when we look at something like this happens, we say, oh, that wasn't that unlikely, but actually it's not, because if each and every 1500 other those incidences, if they happen, then we would say the same thing. All right, so let's move to the next example. So let's move to the another one, example 7.6, where winning the lottery twice. This one. So basically it talks about, it talks about an example of Evelyn Mary Adams, where she was from New Jersey, and she used to play the lottery tickets, and she won two lottery tickets, one of 1.5 million, and another one which was the previous, then this one was 3.9 million jackpot. And the Times Magazine, New York Times, they claim that actually when someone wants to have the win the lottery ticket, so the what are the odds for that? It's about 1 in 17 trillions. They win the prize. That's the odd for one person winning the big prize twice. So but this was ruled out by some statistician. Two statistician, they claim that the fact the New York Times said that 1 in 17 trillion would have the odds of winning two big prizes twice. So uh, they said that if someone is just playing the lottery ticket like Evelyn Mary Adams, so she won twice, because um, it's more likely that if someone who is playing millions of regular lottery, playing millions of regular lottery, and the person is playing it frequently, regularly, then the chances that in its lifetime the person will win two jackpot prizes. So it's just like a long run. You can compare. If it is a short run, then you can predict it, but in long run, at least there will be two incidences where they will be having the big jackpots if they play it regularly, same kind. And same kind of example you can see, there was another jackpot winner, the Robert Humphreys, and he won his Pennsylvania lottery jackpot 2 years later. That was 6.8. So um, that's it for the myth of surprise meeting. Let's move to the next page. So the next one is the myth of law of averages. Here it talks about like casino in Las Vegas. And they talk about one of the example, they talk about if someone is playing a dice game and then a person, she's winning in a row, then we usually say she has a hot hand, that she will keep on winning. And uh, on the other hand, some people say the law of averages that says that it has to be balanced out. Like if someone is winning a lot, it means in order to balance it out, the person has to lose next time. So that's the law of averages, but it doesn't happen. Like if we take an example, if we are tossing a coin 6 times, like here you see if the outcomes were all tail, so next outcome we must, our guess would be okay, it should be a head, but it's not likely to can be, because the coin, it doesn't remember anything in its head, and we can't say that next outcome is going to be a head. But in a long run, yes, we can say that half of the outcomes are going to be, almost half of the outcomes are going to be head and half of the game going to be tail. So if we do 10,000 tosses, and then we have half, 50%, 50-50 outcome for head and tail. So the in that case, the first 6 tosses here where we got all the tails, 6 tails, doesn't matter. So that's the myth of law of averages. Let's move to the next one. So there is an example explaining law of myth of averages. That's basically, we want a boy. Here they talk about that couple, they're just trying, they were trying to have uh, kids, and especially they were trying to limit their family to 4 children, but they all 4 were girls, and they kept on trying, and they had 7 straight girls. And doctor also said that that the law of averages was in favor of 100 to 1, but it doesn't happen. You don't have law of averages where one outcome balances out the other one. Like in this case, there we were talking about if you're getting heads, so next outcome should be tail. No, so here it's not likely that if you're getting girls all the time, so next time you will have a boy. It's not, doesn't apply here, the law of myth of law of average. But in a long run, yes, it's going to be 50-50. So but what happened, the eighth child was again a girl. So let's move to the next part. So next part is probability and risk. Here we talk about, like, usually people, they become very they just try to guess some probability. They have their personal judgment how likely something is going to happen. Like there is an example, usually people, they refuse to fly because they think it's more dangerous than driving in a car. They feel, they find it scarier for them, they think it's risky, and it's not safe for them. But actually what happens, when we, the experts, they collect the data and then try to figure out, that says that flying is safer than driving. But people, based on their intuition, they ignore the data, and their personal judgment prevail on the real fact, and they follow their own personal judgment. So like there is another example, asbestos in schools. So basically people, you may have heard a lot of campaigns going in the past, that about the asbestos in schools, that they're dangerous, the exposure to the students and teachers, it's going to, it's not safe, it's not healthy. But when the experts, they conducted research, they figure out that for asbestos, the if someone works for a school 30 years with the same typical level of asbestos level, so they figured out that for that the probability is 15 in a million. That's the chances that they get a they have a problem because of asbestos health problem. But when the experts, they conducted another research, they figure out if for car accident, is basically 15,000 out of million. So it's more. In asbestos it's 15, and in car accident it's 15,000. So we can figure out that actually the car accident is more riskier than asbestos. So people ignore that. They just look at their intuition, and they keep on working on the problems where they think they can control. So here, uh, people take asbestos so much seriously than driving. So there are three things we can talk about that why they do it. Because when they can control some environment, like when they're driving, they see that they can control it and they can drive safely, so they feel safer. But in school environment where they are exposed to asbestos, they cannot. So, or like if there is a tornado, so they basically get scared, they get anxious and worried, and then they try to control it. So they try to get they try to reduce that problem. Now we have another one is basically they are not able to usually common people, they're not able to comprehend the probability. They cannot differentiate between, like as per the experts said, that 15 per million is for the asbestos and 15,000 per million for the uh, car accident. But they cannot comprehend it, and they just follow their instinct. Their intuition always say that the driving is better, it's not riskier. The car accidents, they're not going to happen that much, but the asbestos is going to um, have a bad impact on their health. So they're worried for that more. So they overestimate where there is a high risk, they just overestimate that, and they underestimate uh, the higher risk. So very small risk they overestimate it, and the higher risk they underestimate. And the last point here we can talk about that the schools um, also asbestos in school, you cannot certainly say that it's going to happen. It's not certain what uh, um, the risks like asbestos in school are not as certain as probability of tossing coins. So they're not exactly same. So these things, like when we get the data about cost, tossing coin can be easily predictable in long run, or we can conduct an experiment. But these kind of crucial and kind of sensitive experiments or research should be, and the data should be always estimated by expert from by doing a lot of complex studies. So we are done by this section. I'll be doing next section in the next video. Till then, stay safe and thank you.